So today we're going to talk about using differential equations to model some real world situations. In particular, we're going to be using differential equations to model population growth. One of the things that is interesting about differential equations is that relationships that we find in the real world are often much more easily expressed in terms of a differential equation than in any other form. And that's really why differential equations are useful. So many times something we want to talk about in the real world can only be described easily using a differential equation. And we're going to see sort of a small example of that today. So what I'm going to do is go over the week 4 lesson 1 template that you guys will be filling in on your own. And I'll just kind of talk about it and go through it with you. So first of all, one way that we could describe the rate of change of a population is the following. We could say that the rate of change of the population is a function of time. Okay, now what that's saying is that the rate at which the population changes depends upon time. Now that's certainly true. However, you can also say that the rate of change of the population is actually a function of the population itself. Now let's just distinguish between these two ideas. The first one, dp dt is equal to something involving t. That would be like at 1 hour into population growth, the population is growing at a certain amount, and then 2 hours into the growth, the population is growing at a different amount, and then 3 hours into the population growth, the population is growing at yet a different amount. That would be describing the rate of change in terms of t, the amount of time that has passed. And surely the rate of change of the population does depend upon time, right? At first, a population might be growing very slowly, but then it sort of, grows very quickly. That tends to happen with, for example, bacteria. However, as I mentioned, there's an alternative way of talking about the rate of change of the population, and that's to observe that the rate of change of the population can in fact depend upon the current population. Now, often what we say is the following. We say that the population is growing at a rate that is directly proportional to the current population. Now, I just want to take a moment to unpack what that means and why it might be plausible in the real world. If you have some population of deer or rabbits or whatever, and you want to talk about the rate of growth of that population, then isn't it true that the larger the current population, the more quickly the population is growing? So if, for example, there are only a dozen rabbits on an island, probably the rate of growth of that population is not very great. It's just 12 rabbits. They're not reproducing very quickly. But if you have 1,000 rabbits or 10,000 rabbits and no constraints, like no constraints on resources or anything else or predators, if you have 10,000 rabbits on an island, then the rate at which that population is growing is going to be a lot larger. So what we're saying here is that the rate of change of the population is in fact dependent upon the current population. Written in the symbols of calculus, that's really saying that dp dt, that's the rate of growth of the population, is, well, proportional to the current population, capital P, really just means that the rate of growth is equal to the current population times some value. That's what direct proportionality means. Okay, so what this equation is really saying is that the rate of growth is going to be equal to some number times the current population. So as the current population P, if the current population P is large, then the rate of growth will also be large. If the current population P is small, then the rate of growth will also be small. That's the physical situation that this differential equation is encoding. So let's take a look at some examples to make this idea a little bit more concrete. Example 1, suppose the population P of Rabbit Island, perhaps more appropriately we should say P of t, capital P is a function of time, okay? Bear that in mind. Capital P is an unknown function of time, which describes the current population. Let's suppose that the population P is growing continuously at a 2% rate. And what I want to do is assume that, what I'm getting at here is that the growth rate is 2% of the current population. That's what I'm getting at with this sentence here. So suppose there are 5,000 bunnies on the island. At what rate is the population growing? Well, the answer is we just have to ask ourselves, what is 2% of 5,000? So 2% of 5,000 is 0.02 times 5,000, which is, if I pull up my calculator, 0.02 times 5,000, that's 100, okay? So that's 100. What that's telling me is that if the current population is 5,000, then you have a rate of growth of 100 rabbits per... Actually, I don't know that the unit of time is given in this problem. I think that t is supposed to be measured in years, so I'm going to assume that the units are rabbits per year, okay? On the other hand, if the current population is only 2,500, then what is the rate of growth? At what rate is the population growing? Well, that's, again, just going to be 2% of 2,500, which is 0.02 times 2,500, which, no surprise, that's going to be only 50 rabbits per year. So you can see that the rate of growth depends upon the current population of the rabbits. Part C, we're given a little bit more information. We're actually given an initial condition. It says, suppose that at time 0, there are 200 bunny rabbits on the island. Let P of t be the population t years later. Write a differential equation for dp dt and solve it to find P of t. What I want you to understand is that saying that, what we've sort of seen here is that the rate of growth is simply 0.02 times the current population. That's what we saw in this first example, right? The rate of growth, 100 rabbits per year, is 2% or 0.02 times capital P, the current population. This rate of growth is just 0.02 times the current population. So in general, the rate of growth, which is dp dt, the derivative of P with respect to time, is going to be 0.02 times the current population. That is our differential equation. And if you notice, it has this form right here. dp dt is equal to k times p for some value k. In this case, k is 0.02, right? So, right, now we're being asked to solve this differential equation. Well, that's pretty simple. We just have to separate the variables. So in order to do that, I will multiply both sides by dt, and then also divide both sides by p. That will give me 1 over p dp is equal to 0.02 dt. So that's what happens if I divide both sides by p, multiply both sides by dt. Now that I've separated the variables, I integrate both sides of this equation. So I'm going to integrate 1 over p, and I'm going to integrate 0.02 dt. So of course I need to find antiderivatives for each of these functions. Well, the antiderivative of 1 over p is the natural log of the absolute value of p. And that's going to be equal to what? Well, the antiderivative of 0.02 is just 0.02 t. And then I remember I need an arbitrary constant plus c. Now, at this point, we use an initial condition, if we do have one, and we do, we have an initial condition. It says that when time is 0, there are 200 bunnies on the island. That means that when t is 0, p, the population, is 200. So, in other words, p of 0 is equal to 200. So we'll replace t with 0, replace p with 200. I find that the natural log of absolute value 200 is equal to 0.02 times 0 plus c. Obviously, this term here, the 0.02, vanishes. And so we find that the natural log of, well, absolute value of 200 is just ln 200. So I find that ln 200 is equal to c. So that's my arbitrary constant. I can now go back to this line here and replace the value of c that I found with the natural log of 200. So I find that natural log of capital P is equal to 0.02t plus natural log of 200. Now at this point what we need to do is solve for capital P, right? Remember that P is the function and T is the variable, so we want to solve for the function capital P. Now the capital P is stuck inside of a natural log function. How do you get it out? Well, you have to exponentiate. That means that both sides of this equation become an exponent of e. We're going to exponentiate both sides by e, the base of the natural logarithm. So the left-hand side becomes an exponent of e. So ln of capital P becomes the exponent of e. And then the entire right-hand side, all of it, also becomes an exponent of e. So as you can see, exponentiating both sides by e means that both sides of the equation become an exponent of e. Now the reason we do that is that this expression on the left, e to the ln of absolute value p, exponentiation by e and logarithm base e cancel each other out. They're inverse operations. So the left-hand side just becomes absolute value of p, and on the right-hand side, I'm not going to make any changes at this stage. Now, there is this issue of the absolute value bars. What do we do with them? How do we get rid of them? There was a comment that we made in one of the previous worksheets which suggested that, or reminded you that when you have a variable stuck inside of an absolute value bars, set of absolute value bars, then really what that means is you have two regular equations. Or to put it a different way, you can drop the absolute value bars, but then you have to slap a plus or minus on the other side of the equation. So absolute value of p being equal to this expression really means that capital P is equal to plus or minus e to the 0.02t plus ln 200. Okay. And there is this question of whether we should be using the plus or the minus. Capital P is either going to be positive e to the blah 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 or negative e to the blah blah blah. It's only one of those and not both of them. There are a couple ways of handling this. One way of handling this is to use the initial condition again. If you use the initial condition again by replacing t with 0 and p with 200, here's what we obtain. 200 is equal to plus or minus e to the, now if we replace t with 0, then this term vanishes and we're left with just the ln 200, and we get this. Now e to the natural log of 200 is just 200, so we obtain 200 is equal to plus or minus 200. Now looking at this equation, you can tell that we should have the plus, not the minus, because 200 is equal to positive 200, not minus. So we should be taking the plus in this equation, and therefore p is equal to positive e to the 0.02t plus ln of 200. Now, you probably could have done that differently without using the initial condition, just by recognizing that since capital P represents population and the exponential function is always positive, you want capital P to be a positive number. So you should be taking the plus sign. But anyway, this is an answer. This is the solution of the differential equation. This function right here is the solution. However, it's not simplified. There is a way of simplifying this expression, which you probably haven't done anything like this since last year in pre-calc, but I'm going to remind you how it goes. The right-hand side of this equation can actually be rewritten as the product of two exponentials, like so. Now, Why is that? Well, look, when you have e to the 1 exponent times e to another exponent, you add the exponents, don't you? And if you combined these two exponents into a single exponent, you would add the two exponents, and you'd be looking at this expression right here. So I hope it's clear that these two expressions, this one here and this one here, are in fact the same. Now, why would you rewrite this expression in this fashion? Because this first term here, e to the ln 200, is in fact just 200. That's just 200. So I obtain p is equal to 200 times e to the 0.02t. And that is the simplified solution to the differential equation. Now, what I want to do is have a look at this, this generalization here. Because what we just did was we solved, what did we really do? We solved this differential equation and we got this solution. Now, we can generalize that quite a lot. Suppose we have in general the differential equation dp dt equals kp. Certainly this differential equation was in that form where k is equal to 0.02, and that's the kind of differential equation that we were talking about at the beginning of this lesson, right? It's the differential equation which says that the rate of growth is proportional to the current population p. Anytime you have a differential equation of that form, the solution is going to be given by the following. P is equal to, first of all, what's this number right here in the answer that we just obtained? What was this 200? This 200 was the initial population. It was the population at time t equals 0. So you can call this whatever you want. Maybe you want to call it c or something, but just understand that the coefficient that appears in the solution will always be the initial population, the population when t is equal to 0. And then it's times, again, looking at the example we just did, e to the power of what? Okay, in our example, 0.02t, but what was 0.02? In our example, that was the value of k, right? If instead of 0.02 you have k, then k is just going to be the exponent that appears here. So this is the solution to this differential equation, as long as we understand that c is the initial population. Okay. All right, so anytime you see a differential equation in this form, rather than going through this pretty annoying process of getting the solution, if you know this formula and you know this correspondence, then you can in fact leap directly to this solution without solving the differential equation directly. Although I would contend it is really important to be able to solve this differential equation manually. So let's have a look at the second example. It says, suppose that on a different island there are 500 rabbits and they grow continuously at a 1.3% rate. How long will it take until the population reaches 2,700 rabbits? Well, this sentence here is telling you that P, the population, satisfies the differential equation dp dt is equal to 0.013 p. That's what it's saying. The rate of growth is equal to 13% of the current population. This differential equation is in fact encoding this information right here. Now, of course, this differential equation is exactly in the form we just discussed, right? It's exactly in this form where k is 0.013. And as I said a moment ago, rather than tediously solving this entire equation again, it would line for line be exactly the same as the one we just did. We'd get the same answer, except a couple of the numbers would be different. We can jump directly to the solution here. We know what the solution is. It's going to be P equals capital C. What's capital C? It's the initial population, right? Which in this case is 500. 500 E to the KT. Well, what's K? In this case, it's 0.013. It's 0.013 T. And that's the solution to the differential equation. And this is the function which can be used, this is the population function. If you want to know what the population is at some later time t, you just replace t with that time value and out pops the population. Now, the question that they're asking us is, how long will it take until the population reaches 2,700 rabbits? Notice they're asking you how long. That's t. They're asking you to find a certain value of t. In particular, what they're asking you for is what value of t will make the population 2,700. So what we can do is replace p, the population, with 2,700 and then solve the resulting equation for t. So let's go ahead and do that. So let's replace p with 2,700. I get 2,700 is equal to 500 e to the 0.013t. And now we just have to solve that equation for t. If you remember exponents and logs, then you sort of maybe aren't too worried about this, but if you're not so good with your exponents and logs, this looks like a nightmare. The first thing you should do is get the exponential by itself, this guy right here. So you should divide both sides by 500. So 2,700 divided by 500, let me see what that is. It's 5.4. So I find that 5.4 equals e to the 0.13t. Okay, so we've isolated the exponential function. Now what you have to do is take logarithms. The reason why is that your independent variable t is stuck inside of an exponent, and the way to get variables out of exponents is to take logarithms. So I'll take the natural log of both sides. I find that natural log of 5.4 is equal to natural log of, well, the whole right-hand side. The good news is the right-hand side cleans up a lot, right? Exponentiation by e and natural logarithm, those are inverse operations. They cancel, so I find that natural log of 5.4 is equal to, well, the right-hand side, the whole thing is actually just the exponent, 0.013t. And then obviously we can solve for t by dividing both sides by 0.013. So ln of 5.4, oops, is equal to, over, nope, let's try that again. ln of 5.4 over 0.013 is equal to t. But we should ask for a decimal approximation of that. Natural log of 5.4 divided by 0.013 gives me 129.72. So about that. So about 129 years, sounds like. Okay, so that's our second example. Well, let's move on to the next section. If you put 50 rabbits on a small island, the number of rabbits might grow at a rate proportional to its current population. That's what we were just looking at in this whole first portion of the worksheet, right? Population growing at a rate proportional to the current population. However, if the population continues to grow at that rate, they will run out of space and food. The growth rate will start to slow down. If the number of rabbits exceeds the resources of the island, the growth rate will become negative and the population will decrease. Rabbits will gently fall asleep and enter dreamland, where they'll dig little rabbit holes to heaven. Okay, so the logistic equation is an improved model for population that takes some of this into account. The two basic assumptions are, it's a typo, should say are, when the population p is small, the population does grow at a rate that feels directly proportional to p. However, there is some maximum population m that the environment can sustain. This is sometimes called the carrying capacity, which you might remember from biology. The population will grow towards that maximum, but as it gets closer, the growth rate starts to slow down. And if the population ever exceeds that maximum population, then it will start decreasing. So the idea is that in the real world, populations don't just grow and grow and grow, right? In the world right now, maybe you have, whatever, say 10 million rabbits, but that doesn't mean that the rate of change of the rabbit population is some astronomical amount, right? there are constraints in the population, like predators and the amount of food available. And so there's some theoretical maximum population that the environment can sustain. And as the population reaches that theoretical maximum, the growth rate slows down. Now the question is, how do you model that kind of behavior? It turns out to be pretty easy to model with the differential equation. And the differential equation which does that is called the logistic equation, the logistic differential equation. And here's the general form. It looks like this. It's a bit more complicated. And I just want to explain why this differential equation models what it supposedly models. What we're looking for is these two things. When the population P is small, the growth rate of the population is roughly proportional to the current population. That's the circumstance we were looking at in the earlier parts of the worksheet. So when the population is small, as a percentage of the total theoretical maximum when the population is small, it's growing at a rate proportional to the current population. But as the population approaches the theoretical maximum m, the growth rate slows down. Okay, if you study this equation, you'll see that it actually encodes that information. Okay, like imagine, let's just take, for example, let's say that m is equal to 10,000. Okay, so you're on an island and the maximum number of rabbits that the island can sustain is 10,000, all right? And let's suppose that k is, 0.02. We looked at that example before. That would give you the differential equation dp dt is equal to 0.02 p times 1 minus, times 1 minus p over m, which is 10,000. Okay? Now, when p is small, that is small compared to the theoretical maximum population, say like 50, we have what? dp dt is equal to 0.02 times 50 times 1 minus 50 over 10,000. What I want you to notice is that when p is small, this term right here is very, very small. In fact, it's so small that we can practically ignore it. So this is approximately equal to 0.02 times 50, and then, well, if this term is ignored, then this whole term in parentheses is really just 1, and this entire expression is really equal to just this first part. Okay? So when p is small, the growth rate is approximately 0.02 times 50, and that's 0.02 p. What that's telling you is that when the population is small, the growth rate is proportional, roughly proportional, to the current population. So when the population is small, the growth rate is roughly proportional to the current population, right? That's like in the early examples that we did today. On the other hand, when p is large, say like 9,999, that's very, very close to that theoretical maximum. What is the growth rate? We find dp dt is equal to, again, I'm plugging into the differential equation here, 0.02 times 9,999 times 1 minus 9999 over 10,000. What I want you to notice in this case, because p is very, very large, this fraction here is practically 1. It's basically 1, which means that 1 minus this fraction is basically 0. So this term that I've highlighted here is very, very small. Okay? We can in fact compute this whole thing if we want. I'll do it on the calculator. 0.02 times 9999 times 1 minus 9999 over 10,000 gives me 0.01999. Okay, that's a very small growth rate. All right, as opposed to this growth rate here, 0.02 times 50 was 1. as a matter of fact, which by comparison is much larger. So as we're seeing, when you get close to that theoretical maximum, the growth rate gets very small. So this differential equation somewhat amazingly encapsulates these two behaviors that we're looking for. This is really sort of like the ridiculous utility of differential equations, that they can easily model things like this. So I just wanted to convince you that, yeah, like indeed, this so-called logistic equation does model the thing that we're claiming it does. So let's move on to an example. Consider Kangaroo Island, whose population's growth is well modeled by the logistic equation shown here. This differential equation is much harder to solve. We won't solve the differential equation in this class. You can solve it, but it requires some techniques that we haven't talked about. But we will work with this differential equation by looking at its slope field and things like that. So let me move this down to the next page. So first of all, the question asks, what two kangaroo populations are stable? Now, let's think about that. Population being stable means that the population is not changing. Population not changing means its derivative is 0. This equation here is a formula for the population's derivative. And we can ask, for what values of p is the derivative 0? If you look at this formula, if capital P is equal to 0, then the entire right-hand side will be 0, meaning that dp dt will be equal to 0, meaning that p is constant. So certainly, if p equals 0, then yep, the population will be stable because its derivative will be 0, which makes sense physically. Because of course, if the population is 0, then there are no kangaroos, they're all dead, no population growth. Okay, that makes sense. Now there's another stable population. It happens when the population reaches the carrying capacity. Okay? In this case, comparing this equation here, right, with this one here, we said that m is the carrying capacity, that theoretical maximum. We can see that m is 50. Okay? So the theoretical maximum is given by p is equal to 50. When the population reaches that 50 number, its growth rate is going to go to 0. And we can just check and see if that's true. If you replace p with 50 in this equation, then this fraction becomes 1. And you have 1 minus 1, which is 0, and the whole right-hand side becomes 0. dp dt is 0, meaning p is constant. So the derivative of the population will be 0 when the population is 0, when the population is 50. Okay, which makes sense. You reach that theoretical maximum, the population is no longer growing. So dp dt is 0. Now, in the next part, we want to sketch the slope field. If you notice, what we have here on the two axes are the following. We have years past 2000 and population. So this is t, and this is capital P. And we're trying to construct a slope field for dp dt. What that means is that at each point on this grid, we're going to make a little line, and the slope of that line is going to be dictated by this formula. What you'll notice is that this formula, as in some of the other slope fields we considered last week, this formula actually does not depend upon t at all. It doesn't. It only depends upon capital P, which means that the slope of the little lines we draw will not change as we vary t, the horizontal axis. They'll only change as we vary p, which will save us a lot of work, okay? I'll do maybe one of these, and then I'll jump to a slide which has all the information filled in, because you don't want to see me plug all these numbers in. So if the current population p is 2, then what's dp dt? Well, if you plug it into this formula over here in the top right, you're going to find it's 2/3 times, let me make this a bit larger, 2/3 times p, which is 2, times 1 minus p over 50, that's 2 over 50. I still need to make this larger. Still still need to make it larger. Wow, okay. Okay, there we go. So if you plug p equals 2 into the formula for dp dt, that's what we get. Let's see what that is as a decimal. So 2/3 times 2 times 1 minus 2 over 50. I get 1.28. Okay, what that's telling me is that when p is equal to 2, the slope of the little line I draw should be 1.28, about 1, okay? So when p is equal to 2, that's like right here. Now, we don't have a t value, but it doesn't matter. This differential equation doesn't depend upon t. So what we're going to do is we're going to draw a little segment here of slope 1.28, a little bit bigger than 1, here, because it doesn't matter what t is, all right? What I'm going to do now is I'm going to jump over to the filled in slide so we can see what that looks like when it's all filled in. So here you can see the 1.28 looks like the previous person rounded to 1, unless I made an arithmetic mistake. But 1.28, pretty close. So you can see they've drawn a slope of about 1. It looks like this slope isn't 1, like it looks flatter than you would expect, but that's because of the scaling of this axis. If you notice, this is over 1 over, and this is up 5. So if you wanted to draw a line that was, say, slope 1, then you would go over this much, but up by only 1/5 of a vertical unit. So that's why they look a bit flatter. So if you plug each of these numbers in, here are the values that you get. And if you plot the slope field, you have something like this. Now what I want to draw your attention to is the fact that we have these two stable population values, right? 0 and 50. Okay. At 0 and 50, the differential equation says dp dt is 0. That means that at these two p-values, the slopes will all be flat. Okay. So at 0, the slopes should all be flat. Horizontal lines here. And at 50, the slopes should all be flat. Okay. Now let's think about what that means. We can use that information to answer some of the questions. Let's consider a kangaroo population with p of 0 is equal to 20. So when time is 0, the population is 20. That's going to be a curve going through this point right here, right? So if we imagine a curve sitting right here and we follow the slope field, it'll tell us to draw it like this. I just follow the slope field. What you notice is that as I approach this 50 value, the slopes start to get flatter, and it starts to force me to slow my growth. And as time goes on, these slopes get flatter, and I'm just gradually approaching that theoretical maximum more and more closely. That kind of analysis is what tells you that the limit as t goes to infinity is equal to 50. Makes sense physically. It's saying that as time goes on forever, the population will gradually approach that theoretical value of 50. Okay? So you go on forever and ever and ever, and you just gradually approach that theoretical maximum of 50. On the other hand, if you go backwards in time to, I guess, the beginning of the universe is what t equals negative infinity would be, not surprisingly, the solution would go to 0. Because as you're going in this direction, here the slope field is pushing you downward, until finally you reach the horizontal slope lines at 0, and you sort of gradually approach 0 as you get closer and closer. With a kangaroo population satisfying this initial condition, p of 0 equals 70, that means that you'd be going through this point right here, 0, 70, and that means that, you know, these lines here are all pushing you downward, right? You saw that at p equals 60, the slopes are negative. They're going to be even more negative here. So those negative slope lines are going to push you downward back towards that theoretical maximum. So you can again see that the differential equation really encodes that theoretical maximum. If for whatever reason the population finds itself above that theoretical maximum of 50, it gets pushed back down to 50. It's really kind of astonishing how much complex behavior can be modeled by the differential equation. Okay, so that is the blank template here. I hope that was useful. I'm thinking maybe I'll do a little bit of the, well, no, I think I'll leave this to you. This video is already pretty long, so I think I'll let you guys work on the assignment, okay? So I hope that was useful.